A warm welcome to you all to the 8th day of the SSERD outreach program. I'm Thejas KB from SSERD. First, let me congratulate you all on the tremendous work on your assignments. You all have been doing very great on all the assignments that have been given to you. We are so happy to go through each and every assignment that you all have been submitting. And wow, they're just amazing. The kind of effort that you all are putting in to do your assignments was really good. And we appreciate your efforts. We'll soon revert back to you on that. And for about 7 days, you have been learning about what's there in the sky and how planets go around the sun, how celestial bodies move in the space. But now, there's a fundamental question that we all have. How do we know that these things are happening in the sky? How do we know that they're true? What instruments are used to prove these things? Well, today I'll be answering all these questions through a series of slides wherein we talk about the history and development of telescopes. So before telescopes, uh, let me all let me ask you a question. Where does the beauty lie? When you look at the night sky, is it the beauty of the night sky, or is it the eyes that appreciate the beauty of the night sky? Well, it's because what we see is what we appreciate. We don't see much of the universe, you see. If there is a beautiful monument in front of you, but if it's obstructed by something, let's say a fog, you won't be able to appreciate it. And that's what happened in the case of early humans. That is, even though there were beautiful stars and all these constellations, even back then, they couldn't observe beyond a certain extent, but still they did make efforts to track whatever they saw. There were many ancient civilizations that did build specific observatories to track celestial events. We have the Mayan civilizations, we have the Incan civilizations, we have the Indians, we have the Chinese. They all were well versed in building monuments to track the astronomical events. Though there was nothing called as telescope, they did have many other instruments to track the movements of celestial bodies and to gather more information about the universe around us. A few of the instruments are right here on the screen. We have the sextant. Sextant was used to look in for the angle made by the celestial objects with respect to horizon and the median line. Using this, they were able to keep track of themselves as to what position we are currently in, or at what particular part of the sky a celestial object would rise or set. Then we have the Volvella, Astrolabe, Antikythera, and Obelisk. Volvella, Astrolabe, and Antikythera were used as star charts. That is, they were used as analog computers wherein uh, people, the astronomers who wanted to track the celestial events, they used to make adjustments in these instruments to know the position of the celestial bodies within the sky. The obelisk, which is uh, and 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 a monument built in Egypt, it was used to know the time using the position of the sun. It is more or less, it works like a sundial. The shadow cast by the obelisk was used to track what time of the day it was in ancient Egypt. Well, even after having these many observatories and so many wide variety of instruments, we still were unable to answer many questions. The questions were like these: how and when was the universe created? Do sun, stars, and planets revolve around Earth? Is Earth the center of the universe? How far are the stars from Earth? What are stars made of? Are the moons orbiting other planets? The answer to these questions did not come in the early part of the human civilizations. These answers came very recently when we look at the entire course of human civilization, somewhere close to 400 to 500 years back. Well, the history of telescopes, it all started with a man called as Hans Lippershey. Well, it is said so that once he was a lens grinder. Once when he was working in his workstation, he found that two children were playing with the convex and concave lenses that they had that was placed there. They were trying to view a nearby clock tower using these two lenses, and they were playing with it, changing their position to enlarge and diminish the image. So he came up with a very simple model of having what is called as simple perspective glasses. He called his instrument as a perspective glass, wherein he had what is called an objective lens, which was a convex lens, and and an eyepiece, which was a concave piece. He adjusted them such that the image that was in front of the convex lens was enlarged somewhere close to 3 to 4 times. However, he couldn't achieve a successful patent over his device, as his invention was easily replicable by others. He did file a patent for this in 1608, but he could not get a patent over this design. However, many others came to copy his invention and started building their own perspective glasses. Well, before moving on to how these telescopes were advanced, how did they evolve, let's answer what is refraction. Because the telescope that Le Perrier built worked on the principle of refraction. The light, let's say, when light travels from one medium to another, light tends to bend depending upon whether it travels from a rarer medium to light denser medium, or denser medium to rarer medium. Water is considered to be optically denser than air. So when light uh, travels from air to water, it bends towards the normal. We have something called as the normal line. Let's say this is a light ray, and we have a medium separating this light ray from the top medium to the bottom medium somewhere in the center. The light that was supposed to travel in a straight path will bend towards this the center line, which is perpendicular to the medium. So this happens when the light is traveling from a rarer medium to denser medium. The bending of light is what we call as refraction, and we make use of wonder pieces called as lenses to make use of this property of bending of light to enlarge or diminish the view that we look at. A simple experiment that you all can perform at home is take a glass of water, fill it with water, and take a pen, pencil, or any object. When you immerse this pen into the glass, you find that the pen is kind of bent. When you look at it at a slanted version, you see that the image of the pen, as seen within the glass, is kind of tilted away from its normal straight line. And also, it is enlarged. This enlargement is due to the fact that the glass that we are holding right now, it's spherical in shape, and it kind of acts like a convex lens, enlarging the image of the pen. So if I hold this pen in behind the glass, you see that the image of the pen is enlarged. So this is what the principle that Hans Le Perrier used to enlarge the images and to build a simple telescope, which he called as perspective glasses. These perspective glasses were initially put to use in order for terrestrial purposes, that is, to watch ships that were sailing into the ship decks to know about their arrival in well in advance. The game changed when it came to Galileo Galilei. When he learned about this particular perspective glasses which Hans Le Perrier had built in 1608, Galileo Galilei, he started working on his own design, and he improved the design such that the magnification was now increased to 20 times. So let's say I have this water bottle. So 4 times this height would be staking this water bottle 4 times one above the other. That would be the height of this water bottle. If I were to use the Le Perrier's telescope to view this bottle. However, using the Galileo's telescope, I'll be able to get a magnification 20 times this original height. That is, staking this bottle one above the other 20 times. Imagine that. It would reach all the way up to the roof of the room that I'm sitting in right now. Well, it was not a very easy job. It was not a very easy path that Galileo Galilei took. for coming up with his own design. First, what he had to do to get fundings to build his own telescope was that to demonstrate that this telescope had application when it comes to trade business. He displayed his telescope in front of the Venetian Senate. He convinced them that these telescopes can play a major role in determining the trade outcomes of Venice. That is, when it comes to spice trades, if a merchant had this particular telescope which could uh, warn the merchants what kind of ship is arriving at the deck, like whether it's a cardamom ship or whether it's a saffron ship or what spice it carried, the merchants would go and buy all those uh, condiments from the ship that did not arrive. Let's say cardamom or pepper. The spice pepper did not arrive on a particular day. That ship was not visible at the given time. So the merchant can go buy all the pepper which is in the market at that particular time. And as the ship will not come, there will be a lesser stock, and he could sell it at a greater price. So he portrayed this application of having a telescope in having the telescopes, and he got wide variety of fundings, and that's how he started improving his telescopes. And the fun fact is, it was neither Le Verrier nor Galileo Galilei who coined the term telescope. It was a person called as Giovanni de Messiani. Uh, Galileo Galilei had presented a telescope version to the institute where Giovanni was working. Giovanni was a Greek mathematician, and to the institute where he was working, Galileo had presented a telescope, and Giovanni came up with this term called as telescope for the device which Galileo had built. Galileo did many great works with the telescope that he had. He pointed his telescope towards the sky, he pointed it at the moon, and he started observing the surface of the moon. So he found that he was amazed at what he got to look at moon by pointing the telescope at it. Unlike what it was believed in earlier days, that moon, planets, and other objects were perfectly spherical and they had no irregularities over their surface, Galileo found that moon surface was irregular. There were patches on moon surface, there were mountains on moon surface, there were craters on moon surface, and he started documenting all these things in the form of paintings. So on the screen, there's a picture of six phases of moons painted by Galileo Galilei. So he started doing a detailed paintings of whatever he used to observe in the night sky, and the moon. These are the original paintings that was made by Galileo Galilei, and this kind of blew everyone's mind. All the people who were who were working along with Galileo Galilei, they could not believe that there were mountains on the moon. And it was Galileo Galilei who also happened to discover that Saturn had a ring system. The drawings that you see on the top of the screen, that is a circle with other two circles next to them, are the kind of image that Galileo was able to make out from his very simple telescope. The magnification of that telescope, the resolution that it provided was not that great, but with whatever he had, he made a point to document whatever he saw. So we get to know that the object that he observed, that is Saturn, had rings, and he painted it well. So the first image, the Saturn's first image that he drew was with a lower resolution telescope. It was not very well built, so he could not make out the finer details of the Saturn. But however, when he improved his design, he found that whatever he found, he started making a detailed description of the Saturn's ring system. And also, it was Galileo Galilei who gave a conclusive proof for the geocentric model. We will see how. Well, during your planetary motion classes, you had learnt about what are called as epicycles, right? That is, when in the geocentric model system, we had all the planets and the sun going around the Earth. But there was something called as the backward motions made by the planets, like the Venus, which could not be explained without having a smaller circle embedded within the larger circle which Venus used to go, the smaller circle called as epicycle. However, if an epicycle existed, It means that from the geocentric model, from the Earth, the first object to orbit the Earth was the Venus. So after Venus comes the Sun. So as Sun is the source of light, it means that only that side of Venus will be able to glow, which faces the Sun. So whenever we have Earth, then Venus and Sun coming in an alignment, we find that Venus should not be visible in the nights in the sky, because we are facing the dark side of the Venus as per the geocentric model. But that was not the case. We were able to observe Venus at all times, so which means that it is Earth and Venus that are going around Sun, and not Venus and Sun that are going around Earth. That is how Galileo Galilei was able to explain that heliocentric model is the right model and not geocentric model. Isn't that cool? That how telescope led to the disproving of the long stood geocentric model and the establishment of heliocentric model. Well, for disregarding the long stood belief of geocentric model, Galileo Galilei was sentenced to trial by the Catholic Church. He was asked not to make such claims that would go against the belief of the Catholic Church. He was also subjected to house arrest for all the claims that he made. Sadly, Galileo Galilei had to spend the rest of his life in house arrest. He could not come out and do research, but however, at the place where he was in, he started carrying out his own research. He started observing sun using the telescope that he built, and he died there. Now we come to an interesting point wherein we learn that when you consider a prism, when you subject that to a light source, let's say an object like this, when subjected to light source, it would split the white light source into different colors, which shows that white light is a composite light and not a single light. And we also find that all these light do not bend at the same angles. We find that the white light, the part of the white light which is made out of the blue light, that is, which has less wavelength, would bend more when refracted, whereas when it comes to red wavelength, that is the longer wavelength, the bending of the light is much lesser. So this means that the light that we are looking in, which comes from the sun or other objects, if that's a composite light, when we start using the lenses to observe them, there arises a problem, what we call as chromatic aberration. So this chromatic aberration is one of the reasons why refracting telescopes was not greatly popular and had a limitation when it comes to astronomical observations. And also there was another limitation, that is the maximum diameter this lenses could have. Well, when we look at telescopes, the distance to which we can observe the night sky depends upon how large the objective piece is, and the larger we go the larger the objective lenses are, we'll be able to resolve much more into the night sky. However, having such large lenses means that the objective piece becomes too heavy. That is, if this were my telescope, if I had a very large objective piece placed at the end of the telescope, it would be very difficult for me to steer the telescope. Even if we overcome the problem of steering a heavy-headed telescope, there's also this problem of sagging of lenses. That is, the lens will start sagging due to their own weight. The lens that we have, a convex lens, due to its heavy thickness at the center, will start sagging, and there will be irregularities in its curvatures. So these were the limitations when it came to refracting telescopes, and both Galileo Galilei and Hans Lippershey developed something called as refracting telescopes. In order to overcome these limitations, Isaac Newton came up with a solution. What he did was, instead of having these refracting surfaces, what we can do is we can have a reflecting surface instead. So that is so because the light will be the angle of incidence and angle of reflection, that is the loss of reflection, will hold very good for mirrors, and it will not vary. It will not vary from one wavelength to another wavelength, and all the visible colors will the angle of incidence and angle of reflection will always be the same. So Isaac Newton's reflecting telescopes overcame the problems of refracting telescopes of the problems like the chromatic aberrations, and the problem of having a very large eyepiece were overcome by our reflecting telescope. So the principle is very simple. The first reflecting telescope which Isaac Newton built had what is called as a spherical concave mirror, wherein the incoming lights, the parallel incoming lights would come and hit the spherical mirror, and it would be focused into the eyepiece. So once they were focused into a particular reflecting surface, that the secondary mirror, it will be reflected back to the eyepiece, wherein the person who is viewing will be able to see the image from the eyepiece. Well, this design was modified, and there were many versions of reflecting telescopes. People came up with many other designs, but however, Newton's reflecting telescopes proved to take over the refracting telescopes, and mostly all the telescopes that we use for observations today, for major observations, come from the reflecting telescopes. They are of the type reflecting telescope. And then after many years, that is somewhere in 1789, Sir William Herschel built what is called as the 40-foot telescope. So with the commencement of the 40-foot telescope, the era of large telescopes started. Sir William Herschel was the person who discovered the planet Uranus and the moons of Uranus. You all might be knowing about his achievements. The 40-foot telescope that he built, it was due to the fact that the more deeper that we wanted to look in the night sky, the more the better the resolution that we wanted, we had to go in for a larger telescope. He realized this fact, and he built this 40-foot telescope. However, he used a smaller version of the telescope to discover Uranus because it was very difficult. He soon realized that it was very difficult to steer this large telescope that he had built. But still, it did not discourage his experiments. And also, we must thank Sir William Herschel for doing wonderful experiments with respect to spectroscopy as well. We all know that electromagnetic spectrum varies. It starts from the gamma rays and goes all the way till radio waves. And the part that we can see, that is the world that we are seeing right now, makes a very minute part of this entirely large spectrum. So what we see, the world right now, may not be the world if we were able to perceive the world in terms of UV rays, IR rays, radio waves, X rays, and all the entirety of electromagnetic spectrum. The world as we look in might change. So the sky, this applies even for the sky. So the stars and the objects, the stellar objects that we are looking at, they don't just emit the visible light. They also emit lights in IR regime, IR spectrum, radio wave spectrum, UV spectrum, and also X-ray spectrums. So in order to understand better about the universe, we should be able to look at the universe in all these spectrums. So that's when Sir William Herschel realized that there was scope in invisible astronomy as well. So observing the universe in the non-visible regime is what we call as invisible astronomy. So William Herschel actually, he also realized, while when he splitted the pure white sunlight from the sun into its constituents, he did an experiment. That is, he took a thermometer and he started measuring the temperature of each of these lights. And when he went beyond the red light, he found that the temperature was still increasing. So that is when he realized that there are light regimes even after the visible spectrum. So the importance of observing the universe in the invisible spectrum was understood in the 20th century. And It is when we started observing the universe in the radio wave spectrum, infrared spectrum, X-ray spectrum, UV ray spectrum, and gamma ray spectrum as well. The first that came when it comes to invisible astronomy, the first kind of telescopes that came were radio telescopes. Well, there's an interesting story when it comes to radio telescopes. They were actually made in an accidental fashion. It was somewhere in 1930s, and Carl Jensi, who was working in Bell Telecommunications, he was assigned a task of looking for radio waves to communicate, make phone calls overseas. While he was investigating this particular case, he used to find that all the time there used to be some kind of static noise that were being recorded. So he set up an experimental setup, and he set up an experimental which is known as a merry-go-round setup, wherein he placed the uh, radio receiving device, and he rotated the device 360 degrees, and he started looking for the sources of the radio waves, the radio wave static noises. And he soon realized that there was this one constant noise which was constant in all direction, and which was speaking at one particular direction. That is when he realized that radio waves were being emitted from the universe, and he wrote a paper on it. And that's where it all started for the radio astronomy. People started looking in for infrared ray, X-ray, UV ray, gamma ray telescopes, and all these things after the establishments of radio astronomy. So when it comes to telescopes, we have different kinds of telescopes. Or we have the hobby telescopes that we use for looking at the night sky, which is movable, and we have it at our own conveniences. But when it comes to research, we have what are called as ground-based observatories. In ground-based observatories, we have very large telescopes placed at a ground station, and the places for these stations are very remote. That is, they're far, far away from the human population and the urban areas. It is so to avoid the light pollution that we have in the urban concentration. They are situated in very remote areas that have very dark sky and where the stars are visible. And also they are preferred to be located at a higher altitude. Why higher altitude? I'll answer to that question in some time. We have what is called as adaptive optics. Adaptive optics is when you look at the night sky, you see that the stars twinkle in the night sky, and actually they don't. The twinkling of the stars in the night sky is caused by the fluctuation, the turbulences in the Earth's atmosphere. Consider that you were situated at the bottom of this class, and the the surface of this water is the upper extreme of the atmosphere. If that were to be the case, if you were to be located at the bottom of this glass, you will see that as and when there is fluctuation in the surface of the top of the glass water, the image that is formed beyond this, that comes from the region beyond the surface, will also start deteriorating. It also starts fluctuating. There will be some perturbation in those images. And that is what happens when it comes to atmosphere as well. That is, we are immersed in a sea of air, and there are some fluctuations happening at the top layers, and these fluctuations are causing the images coming from the light which are emitted from stars and other planets to fluctuate. But as the light from the stars are too distant, the fluctuations are much, much, much evident, and we that is the reason why we find that the stars are twinkling. This is a hindrance when it comes to observation, because these turbulences will prevent the scientists and astronomers from getting the actual image of how the objects, the celestial objects, look like. So in order to correct these fluctuations that are caused by atmosphere, the turbulence caused by atmosphere, we have what is called as adaptive optics. In adaptive optics, we have a computer system, a pneumatic system, wherein the disturbance in the incoming wavefront is realized, like what kind of disturbances are being formed within the atmosphere are sensed by a computer system. It corrects that incoming wavefront using a particular rubber lens that can be changed that will be changed such that it would reflect the incoming disturbed wavefront and turn it back into a corrected wavefront. That is, the light waves that are coming in a distorted fashion will reflect over this particular corrective surface, which is corrected by a computer. It will reflect on this, and the light wave will again become proper, and that is used to view the actual image of how the objects in the sky look. At the bottom of the screen, you find the images of how we get to see Saturn and other star clusters when before having adaptive optics and after implementing adaptive optics. Before implementing adaptive optics, the images are very blurred and so they're unclear. After having adaptive optics, that is after correcting the distorted light waves that come from the atmosphere, we have a better image. We are able to produce a better image. So as I was telling you, when it comes to telescopes, the larger the diameter of the telescope, the better we will be able to resolve the images that are coming in. However, we can't have such large dishes. What to do in order to image something that is very far away? So in order to overcome this limitation, we employ what is called as interferometry. Before jumping into interferometry, we must understand what is called as interference. Let us consider a light wave. This is a light wave from source 1, and there's also another wave from source 2. You find that the crust and the crust and the trough and the trough of these two source images, they are in the similar fashion. So when these waves get added together, they result in an amplified wave, which is much stronger than the original wave. So this intensification is what we call as constructive interference. That is, we have light waves being added up in such a fashion that the outcome, the resulting wave is much brighter than the original ones. What if instead of having these constructive interference, what if the waves were out of phase? When we have a crust, the second source would give a trough. When we have a trough in the first source, the second source will give a crust. What will happen if such waves are added? It will cancel out each other and we will find no light coming out. So that will lead to a dark patch. So this is called as destructive interference. Using these principles, scientists were able to come up with a method to uh, resolve the images that we obtain from faraway stars. Imagine this. We have our two eyes. Close one of the eyes and try looking at an object. Try to get its exact position. You won't be able to. Now open both the eyes. You'll be able to locate the exact position. That is because we have image, the light source coming from this image and light image that is being traced by both the eyes are being overlapped in our brains together to get a perception of depth, and we are able to resolve a final image and we are able to locate it. Though there is a gap between our two eyes, we have the ridge here on our nose that differentiates our two eyes. There is a gap between our two eyes, but still we don't see two images. We see both the image seen by this our right eye and the image seen by our left eye are merged together to give a single image. So this is the same principle that the scientists use. That is, they have multiple arrays of telescope within a given apertures, so that all these single smaller telescopes act as eyes, and the images obtained by all these telescopes are together merged later to get a larger image using the techniques of interferometry. Using interferometry, we'll be able, knowing the angle at which all these telescopes are placed, will be able to detect what is the delay in receiving the light by each of these telescopes. So interferometry and adaptive optics are some of the techniques that are employed in the modern day observatories to overcome the limitations of the atmospheric turbulences and resolving the images that are too far away. Now let us look at some of few of the major observatories, famous observatories that we have. The first one comes that we speak about is the Keck Observatory. Keck Observatory happens to be a twin observatory wherein each telescope is somewhere close. It watches the night sky in the visible spectrum. So yeah, it has a diameter of 10 meter. So constructing a telescope with a very large diameter is difficult because even if we are to make a spherical mirror of such large diameter, the chances of them breaking is very high because due to fluctuations in temperature, humidity, and other conditions, the reflecting surface that we create in the larger we create, the chances of them distorting, the surfaces being distorted, they become very high. So scientists and engineers came up with a technique that is they started making smaller multiple mirrors being arranged together to form a very large telescopes. And these techniques are employed in Giant Magellan Telescope. This Giant Magellan Telescope has an aperture somewhere close to 24.5 meter, which is larger than the aperture that we have in Keck Observatory. So the larger the diameter of the telescope, the more is its collecting area and better is its resolving power. Then we have what is called as Atacama Large Millimeter Array Telescope, which is famously known as ALMA. These telescopes are located in Chile. These telescopes are radio telescopes. They look like dishes that are mounted on the top of our houses to receive the network for our TV connections, but they are used for astronomy. Trust me. These array of telescopes are placed to monitor the night sky to obtain the radio signals from different parts of the sky. And these radio waves are together then collected using the techniques of interferometry that I spoke about and to image the night sky. Most of you might be wondering that which is the largest telescope that we have on Earth? How large it is? To answer this question, we have what is called as the 500-meter aperture spherical radio telescope, which is in short known as FAST. This FAST telescope is in China, and it is the largest single dish telescope ever built by humans. It is 500-meter wide. Imagine that it is 500-meter wide, and that is half a kilometer. I mean, traveling from one part of the telescope to the other end, it's close to half a kilometer. And the second largest telescope, which is also a radio telescope, by the way, is in Puerto Rico, and it is the Arecibo Radio Telescope. It before the 500-meter aperture spherical radio telescope, which was inaugurated in 2016 or 20, it became operational in 2019, I guess. Yeah, in 2019. Before that, we had the Arecibo Radio Telescope being the largest telescope in the world, and the diameter of this telescope is a whooping 305 meter. A whooping 305 meter. Imagine that. It would take huge amounts of efforts to construct telescopes of such large length. And all these telescopes that we saw now, the ground-based telescopes and the radio telescopes that we saw now, they work on the principle of reflections. They are not refracting telescopes, they're all reflecting telescopes. So we have refracting telescopes and reflecting telescopes, and most of the telescopes that we use today are reflecting telescopes. Then when we talk about observing the night sky, as I told you earlier, atmosphere is one of the barrier, like in it disturbs the images that we get to look at, and it also prevents other wavelength wavelengths from reaching to the ground of the earth. It filters X-rays, it filters UV rays, it filters gamma rays, It also filters infrared rays to some extent and also long wavelength radio waves. So if we were to look at the night sky in these spectral regimes, it will be impossible to do so from the ground. So in order to do that, we have to go somewhere above the atmosphere, wherein the gamma rays, X-rays, and UV rays from celestial objects are not filtered. That is, we are still able to get these rays from those objects uninterrupted. So in order to do that, scientists and engineers have come up with various techniques. And in one such technique, we have what are called as airborne observatories. Sophia telescope, which was launched in somewhere in 2009 or 2010, in this airborne observatory is used to watch the night sky at an altitude of 13 to 14 kilometer above the ground. So this aircraft takes off from the ground, and the open pit you see on the aircraft is where we have the telescope being placed pointed towards the night sky. The aircraft is airborne for somewhere close to 10 hours, and scientists observe the night sky for 10 long hours using this airborne telescope to observe the night sky in the UV and IR regimes. Sophia telescope is a wonder as in such with respect to technology. The aircraft that is being used for Sophia telescope is a Boeing aircraft, and yeah. So in order to go somewhere beyond the realms of Earth and to observe images that are coming from far away universe, be unfiltered, we have what are called as space telescopes. We have Hubble Space Telescope, our beloved telescope and the most popular telescope you all would have heard of. It has helped us crack some of the most mysterious cases of the universe, from letting us know how the stars evolved from their creation to their birth, and how stars are born, how there are existence of exoplanets orbiting other stars, and also how uh, how a star dies. All these things are imaged by Hubble Space Telescopes, and it has helped astronomers uh, for in a tremendous manner. This is a space telescope which is placed in the low Earth orbit. It was placed in the year 1990. Hubble Space Telescope's diameter, the aperture, is not very great. We have telescopes on Earth which are somewhere close to having an aperture somewhere close to 24 to 30 meters, but Hubble Space Telescope has a humble aperture of 2.4 meters, just 2.4 meters. But still, as it was located in space, as it has access to a wider regime of spectrum in electromagnetic spectrum, it was able to capture images that most of the ground-based telescopes could not. So the image that you're looking next to the Hubble Space Telescope is what is famously called as the Pillars of Creation. This Pillars of Creation comes from the Eagle Nebula part of the night sky. So it is called Pillars of Creation because you see the uh, columns of dust, gas clouds rising there, which is just about to form a new star, being and these stellar formation are being lit by the light source from the nearby stars. And this is a spectacular image because you don't get to see stars being born every day. So now we come to what we have for today's assignment. Today's assignment is take few images taken by Hubble Space Telescope, retrieve it from the NASA website or from the Hubble Space Telescope's uh, gallery, and write something about that image, where from which part of the sky it was taken, what is the importance of that image, what can you make out from those images. Write a short note on it, take two images, and do send it to us in the homework section. That is your assignment for today. There are many other space telescopes as well. We have the Chandra X-ray Observatory and the James Webb Space Telescope. Chandra X-ray Observatory, this particular space telescope was dedicated to scan the night sky in the X-ray regime, and it is named after the famous astronomer Dr. Subramaniam Chandrasekhar, who gave us the Chandrasekhar limit, which talks about how stars evolve depending upon their masses. Now, next in the picture, we have the James Webb Space Telescope. James Webb Space Telescope is yet to be launched into the skies. It is yet to reveal. It is yet to scan the skies, and it is yet to reveal mysteries of the night sky. It is scheduled to be launched in the next year, 2021. It will be operational by then, and we hope to get some very good images from the James Webb Space Telescope, and we are hoping that it will shed more light about the exoplanetary systems. That is, the planet revolving around other stars in other constellations and other parts of the skies. Okay, now we come to the part wherein we compare the different sizes of diameters of the telescopes that we have. As you can look at the screen here, Hubble Space Telescope has a very small diameter, and it is somewhere close to 2.4 meters. And at the bottom, you have James Webb Space Telescopes. And most of the space telescopes that we see, they don't have a very large diameter, because the larger the diameter, it becomes very difficult for us to place them in the orbit. So the diameters, the apertures of these telescopes, the space telescopes, are much lesser than the apertures of the ground-based telescopes. Most of the ground-based space telescopes, that is something like the extremely large telescopes, the 30-meter telescope, and the giant Magellan telescope, all these telescopes have they have a much larger aperture compared to the space telescopes that we have now. So now that brings us to the part where we will have a quick recap session of what we learned today. The telescopes, the origins of telescopes started with Hans Lippershey in the year 1608, wherein he came up with his perspective glasses. Then we have Galileo Galilei improving upon Hans Lippershey's design, and in 1609 he comes up with his own design that can magnify the celestial object somewhere close to 20 times their own size. After the problems faced by the refracting telescopes were understood, Isaac Newton came up with his own design of reflecting telescopes, that is, using mirrors to look at the objects, to magnify the objects, and that was in the year 1668. Then came Sir William Herschel, who built the 40-foot telescope and led to the advancement of large aperture telescopes. Then we started building very large ground-based observatories like the Keck Observatory, and the Giant Magellan telescopes, the Arecibo radio telescope, and the FAST telescope, and many more. And we came to radio astronomy, and now we are in the era where we have telescopes located in the lower Earth orbit regimes scanning the night sky for us. For most of you who are pursuing hobby astronomy, a hobby telescope is something that you all dream to possess. So now, when it comes to hobby telescopes, we have different parts in a hobby telescope. It is very important to understand how it works. We have a tripod to make sure that the telescope does not move and it is located in a proper place, providing us stability to look at the part of the sky that we are looking in. And we have the aperture, that is the objective, which will take the incoming light and will send it to the magnification, will magnify that. And then we have the eyepiece, and we also have what is called as the adjustment screws, using which we can adjust the magnification that we want, and depending upon additional components that you all want to have, there are something called as the finder scopes that will help you in fixing a target, looking for a particular object in the sky. And you also have the equatorial mount for you to give the angle of inclination, and setting the angles of the telescope with respect to the horizon and the equatorial meridian. Now, For those of you who are interested in buying a hobby telescope, here's the link. You can all go to Edge of Space website, wherein you'll be guided as to what kind of telescopes you can buy, whether you should be buying a refracting telescope or a reflecting telescopes. When it comes to refracting telescopes have they have a lower maintenance, and they're they they're best suited for astrophotography. Reflecting telescopes are a bit much difficult to handle, but they don't have the problem of chromatic aberrations and other things. But for there are filters and other components to correct the chromatic aberrations when it comes to refracting telescopes. Now, before taking the call off, we have what is called as the Stellarium app, where using which we can uh, learn about what's there in the night sky, what particular object to watch in the night sky, and where we can find them. I call upon Nikita now on the screen to tell us more about that. Nikita, will you be guiding us through how to use the Stellarium app? Oh, yeah. Okay. Nikita is lost in finding a particular object in Stellarium. So I'll present it to you all. We have Stellarium application right here. Let me just add it to this. Okay. Okay. This is the Stellarium app, wherein depending upon the location that you are in, you'll be able to look at what constellations are there visible in the night sky, what objects are visible in the night sky, and at what directions. Now I'm in the location that I'm in will be showed here. This can be changed based on wherever you're located at. You can do those settings here, and it also provides what are called as the constellations, constellation art, atmosphere, landscapes, and it has multiple options. If I deselect the constellations option, the lines that used to show me what kind of constellations these stars make will become invisible. So right now I'm looking at the south part of the sky as it is visible from the location where I'm situated at. Uh, you also find the names of the stars, some of the major stars in the night sky. Now, once I select the constellations again, the constellation lines come back. Isn't that cool? Now, I'm looking at the west part of the night sky. We have the Libra constellation, which is located at the west part of the sky, at the location that I'm in right now. There's something called as the constellation art, which can be overlaid over this to look at these lines as to how they look in terms of art. Yeah. Next, for those of you who are interested in uh, getting images from observatories, but you don't have a telescope, there's nothing to worry. There's something called as Micro Observatory Project by NASA, and in here you can operate your own operate request for operating your own telescope, or else you can ask NASA to send in an image of a particular solar object or a particular celestial body. So what you have to do is go to the micro observatory splash page of NASA and select observing with NASA. Then in that a new page pops out. You have to go to control telescope and select which object that you want to view. For instance, I want to check out moon today. I'll select observe, and the control telescope will take me to the next settings, wherein I'll be selecting the kind of views that I want, the exposure time I want, and the kind of filters I want. Once I'm done with selecting all these things, let's say I'll be selecting zoom view, an exposure time of 30 seconds. Okay, an exposure time of 1 second with a gray filter. Now I'll select continue, and all I have to do is provide my email address, choose an age that I belong to, choose my gender, and choose the territory where I come from. How often do I use telescopes? And these things are not mandatory, but yeah, you can fill in all these detail and select submit. Once you're done with it, all the settings will your request will be submitted to NASA, and the image will be taken out through one of the telescopes in for the day, and the image will be mailed in for analyzing to you to your mail ID. You can get those images and analyze those images in the very same website. uh, it is called as by selecting the analyze image toolbox. Okay, that is for now. I hope you all learned something about telescopes, how they work. Now we have the session wide open for the question answers. Let's look in for what kind of questions we have in the chat box. Okay. How can we steer a 40-foot telescope? Wow. Yeah. Steering a 40-foot telescope is not a problem in the modern days. Right now, we have many mechanisms, hydraulic mechanisms, and all those motor-driven mechanisms using which we can control the steerability of these telescopes. But however, when William Herschel had built it somewhere in the 18th century, it had to be done manually. So that is the reason why he couldn't use his telescope more extensively. Why the pen looks in one side, keeping pen it looks bigger in the other side. Okay. Yeah, you mean about this experiment, right? Like why the pen looks bigger when it is placed behind this glass filled with water. So it is as I told, as I was talking to you all about the the principles of refraction. When I place this pen behind this glass, the light that comes the light which is being reflected through this pen goes through the glass and gets refracted. It gets refracted, and as this is a spherical surface, we have the light being diverged. So as in when the light diverges, it comes and makes an enlarged image in the front, and that is why we see that this particular pen gets enlarged. Even the same thing happens with the magnifying glass. My eyes they look very normal right now. So if I hold it against a magnifying glass, they start looking bigger, 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 and they come back to normal. Yeah. Why can't we make a telescope that can go see our galaxy? Oh, we can make a telescope that can see the whole of a galaxy at a single time, but it's gonna take very long time. Like we have to make the telescope, send it out in space, then it has to travel all the way where it would get a wide field to cover to be able to view the entire view of a galaxy. So that's a long process, and oh, yeah, we are not much interested in that as of now. But you can try. You can give out that idea to NASA or ISRO or any other space agency, and they might be interested in coming up with such a telescope. What is the difference between telescope and binoculars? Okay. When it comes to telescope, telescope has a single eyepiece. Okay. In binoculars, we have uh, two different eyepieces coming together, and telescopes can be either astronomical or terrestrial. Terrestrial telescopes are used to view images that are on the ground to get an enlarged image, a closer image of the objects that are on the ground. Astronomical telescopes are used to view at the night to get the magnified images of the night sky. In binoculars, we have two telescopes being held together, so it's called binoculars, two oculars, two eyepieces. Is there any satellite spaceship to find other living beings in universe? Okay. The question says there's a question: is there any satellite, spaceship, etc., successful to find other living beings in universe? As of now, we haven't found any other life on the exoplanets or any other planets or any other star system. But life beyond Earth is something that we are still searching. So it's still in progress. Obviously, we having life somewhere out there, but we are still looking in for proofs. But there are no mission. There's no mission that has actually confirmed the any life on other planets or other bodies. Okay, what? Why do we need telescopes? Okay. Why do we need telescopes? It is to observe. We need telescopes because it is what our eyes can see is very limited. So we can make out to some distance, and beyond that we won't be able to make out anything. So stars and galaxies are located far far away, and one other cool fact is that, if these stars are located somewhere beyond 300 kilometers, 3 lakh kilometers, the light coming from those objects would be delayed by 1 second. Imagine this: the sun locate the light from the surface of the sun. It takes somewhere close to 8 minutes to reach from the surface of the sun to us. So it means that if sun were to vanish right now, we won't be able to realize that the sun has vanished until the until after 8 minutes. So if a star is somewhere close to 4.2 light years away, if that star were to explode right now in the night sky, in wherever it is, we will see that explosion only after 4.2 years, because the light from that particular explosion will take 4.2 years to travel from that star and to reach to us. So that is one of the reason why, uh, to look at all these things, we need instruments, and to record them we need instruments. That's why we need telescopes. And telescopes can see something beyond what we can see. It can look back into time. In a way, telescopes are key to are key to watching the past. That is, using telescopes we can look deep through the space, which means that we'll be looking back in time. Okay, that is for today. I hope you all will complete your assignments for the day. Tomorrow, for tomorrow's session, we have space medicine and space agencies, and it will be by Rutuja and Marcelo. And thank you all for joining us. You all are doing a great job on your assignments. Hope you did learn something about telescopes, and do check out the links that have been posted in the resource section. It will be updated by today. Check out all those links, and you'll learn more about telescopes, and you'll also find guides to what kind of telescopes you can buy, and also the micro observatory and the stellarium applications that we showed right now in this video. The links to them will also be posted in the resource section. Do check them out. Thank you for joining us. This is Thejas signing off. Bye bye.